Yeah, I'd just like to introduce Brian. Brian has been one of the pioneers of the deep network usage in speech recognition, and he's kind of an institution at IBM. He's been there for about 20 years now, maybe celebrating his anniversary, and he's also now the leader of the entire speech technologies research group. He's a distinguished research staff member and in IBM Research AI, and so he's very busy nowadays, but he's going to present on some interesting insights about deep network optimization, and well, I'll let him take it away if he is ready.
All right, so this is going to be a two-part talk. The first part is going to be eminently practical, which is how do we go about training really big deep neural network models on lots and lots of speech data for the purpose of doing acoustic modeling in automatic speech recognition. And then the second part is going to be quite theoretical, talking about some joint work with researchers at MIT on trying to use an information theoretic perspective to understand information processing within deep neural networks. Okay. So the first part, this is joint work by a large number of people at IBM Research, the leaders being Wei and Xiaodong, or two of my colleagues that I'm really privileged to work with. And this is describing work that's been published in both ICASP and InterSpeech this year, and hopefully ICASP next year if the reviewers like the latest submission. So what's the problem setting? We all know, I think, at this point, if we have looked at speech recognition at all, that deep neural networks have sort of conquered the field. Any state-of-the-art speech recognition system is going to use some form of deep neural network acoustic model. And what I'm going to talk about here is specifically a large bidirectional LSTM-based network. The problem setting is going to be the Switchboard 2,000-hour training set. This is a standard training set for speech recognition. It's a large collection of transcribed American English conversational telephony speech. For testing, I'm going to focus on a specific test set from year 2000 DARPA evaluation. And it's broken down by two different data sets. One is a Switchboard collection, and one is a separate collection called Call Home. I should note that although this test set is really, really standard in the field, it is somewhat flawed because some of the speakers in the Switchboard portion of this test set, actually overlap speakers in the training set. So the error rates on the Switchboard part are unrealistically low, but because everybody reports on it, that's what we're going to do. The model in question is a deep bidirectional LSTM network. This is actually using not the latest fashion, which is end-to-end speech recognition, but a hybrid model where you have audio features come in, and what comes out is a posterior distribution over context-dependent hidden Markov model states. In this case, 32,000 different HMM states. It's a windowed LSTM, which means that it only looks at a finite length of the signal at once, in this case 21 frames, 210 milliseconds. We use three different feature representations, Mel spectra with deltas and double deltas, some speaker-adapted features, and then a 100-dimensional I vector, which is just carrying speaker information. We've got 6 layers of BLSTMs, 512 units per direction per layer, and then a 256-dimensional bottleneck between the last layer of BLSTMs and the output layer. We've got 43 million trainable parameters in all. And we're just going to look at cross-entropy loss. Baseline model, which is trained serially on one GPU, gets what's basically state-of-the-art performance, 7.5% word error rate on Switchboard, 13% word error rate on Call Home. It is possible to get lower numbers on these test sets by doing things like neural network language modeling or using sequence-oriented losses to do the training. But if you restrict yourself to frame-wise cross-entropy and decoding with just a large 4-gram LM, this is about as well as you can do. And this is great, but it takes 8 days to train one of these things on a single GPU, which makes it really, really hard to do research because every experiment takes 8 days. So this means that we need to look at ways to speed this up. And the most obvious way to do it is to take advantage of parallel hardware. Specifically here, I'll be talking about data parallel algorithms where we split up the training set amongst multiple GPU processors, and then the training algorithm operates in parallel in those processors and needs to do some sort of synchronization. And just to compare to another task that people have looked at parallelizing, which is the ImageNet image classification task, it's interesting to notice that in some ways the speech task is harder. We have about 1.5 times as many parameters in this VLSTM network as you do, say, in a ResNet 50 model. We have 32 times as many classes, and the distribution is very, very skewed in the speech case, whereas it's almost uniform in the vision case. And if you look at how much computation you do in the network per training batch of data, you find that there's about 3 times as much computation in a ResNet as there is in one of these VLSTM networks. So what this means is that the trade-off between communication and computation, if you do a parallel training, is a lot worse in the case of the speech model. So I want to go through a few different algorithms for doing parallel training. The most popular one at this point, I'd say, is synchronous parallel stochastic gradient descent. In this setting, you have some number of workers, which are portrayed over here. You split the data amongst them, and then each one of them, in the inner loop of the training, grabs some sample of data from the data set, computes a gradient of the loss function, and then the workers synchronize the gradient. So they do an all-reduce, which leads to every worker having a sum of the gradients from all of the workers. Then each of the workers does a weight update because they all have the same gradient, they all have the same weights after the update, and they just iterate. And I should note in this diagram that the arrows here are portraying communication patterns, but not the actual implementation. So in most high-performance computing systems, the GPUs will be arranged in just a ring architecture. You won't have these direct connections across the center. But the picture here is to say that really you do need all-to-all communication to accomplish the all-reduce. So this is a really popular algorithm for a number of reasons. There's complete synchrony. All of the workers have the same weights. You're always computing gradients with the most recent version of the weights, so you don't have any problems with staleness. It's very simple to produce convergence conditions and guarantees because this algorithm is identical to doing serial gradient, stochastic gradient descent. It's just that you're splitting up the gradient computation amongst multiple workers. But of course, there's some disadvantages. If you're in some sort of a cloud computing situation where these workers may be residing on servers with different workloads, then you'll find that at this all-reduced step, you have to wait on the slowest worker, and so that can actually slow you down. And there's also a really high communication cost because you have this all-to-all communication pattern, and it's within the inner loop of the optimization. Okay. So these disadvantages have inspired people to look at a number of alternative approaches to doing optimization. One of the most popular examples is what's called asynchronous parallel stochastic gradient descent. So what happens here is in addition to a set of workers, there's also a parameter server, which is responsible simply for maintaining the network parameters and performing updates. So the way this works, again, data is split across the workers, and then each worker executes the following steps. They request the latest version of the weights from the parameter server, they compute a gradient, and then they send that gradient back to the parameter server. There's no coordination between the workers. The parameter server does the update, so every time it gets a gradient, it does a gradient step on whatever its weights are, and then when it gets a request for the weights, it sends those back to the worker. So it's great. There's no need to do any synchronization amongst the workers, so this works really fast. The disadvantage is that if you have a slow worker, it may be computing gradients with a set of parameters that are stale, that actually were correct 2 or 3 or 4 updates ago or even longer. This can lead to slower convergence, and potentially the parameter server can be a bottleneck if you have a lot of workers, although there are methods, say, where you will split the parameter server amongst multiple machines to help with that. And this is the basis of, among other things, Google's downpour SGD system. So it's a good algorithm and quite well studied. The approach that we're going to look at, though, is a little bit different. and it's what we call asynchronous decentralized parallel stochastic gradient descent. So here, we've eliminated the parameter server, and instead we just have peer-to-peer communication amongst the workers. So every worker will only talk to some small set of what we'll call neighbors. And in fact, in the most common setting, we simply arrange the workers in a ring, and each worker will only communicate with its two nearest neighbors. The algorithm here, again, we split the data amongst the workers. Each worker will sample a mini batch, compute a gradient. It will then request the weights from its neighbors. I've notated this to be general, but usually this will just be 2 weights. And then it does a weight update where it averages the weights from its neighbors with the weights it has, and then does a gradient step on that. And then it will communicate the weights back to its neighbors. In terms of implementation, the gradient computation and the communication are usually executed in separate threads, so they can be potentially running in parallel with one another. This is a nice algorithm because we have limited synchronization costs. There is a theoretical convergence guarantee, and we have relatively limited staleness because we only have this very local communication. One of the disadvantages, though, is that there is a trade-off between communication and convergence. So in the analysis of the convergence of the algorithm, you can show that basically the more neighbors you have, the more communication you're willing to spend, the faster the algorithm will converge. So in the setting where we only have 2 neighbors per worker, we often have to run a few more epochs of training to get competitive word error rate results. But this is the one that we're going to use. Okay. So if you're going to make this work and you're going to use a large number of workers, you necessarily have to have a large number of samples in each batch so that you can take advantage of the GPU performance and get a better trade-off between how much compute you're doing versus how much communication you're doing. So the chart on the left here is showing a simple analysis for training on Switchboard 2000 case, where on the left-hand side we're showing the number of hours of computation you need for a given batch size on a single GPU, going from 32 in powers of 2 up to 1,024 samples. And then the orange bars, which correspond to the right-hand axis, show the amount of communication bandwidth that you need between GPUs to basically break even, so that you're spending 50% of your time on communication and 50% of your time on computation. Basic message here is that the larger batches make more efficient use of the GPU resources. The amount of time that you need drops down, although you can see it eventually starts to tail off. And the larger batches also lead to much less communication costs. So you can get by with a less expensive, slower network between your workers. But as people have observed for quite a while, often stochastic gradient descent doesn't converge as well in terms of things like held-out loss if you are doing updates on large number of batches. There's a number of reasons for this. For one thing, you simply are doing fewer updates overall on your model, and also there seems to be some evidence that the variance introduced by having stochastic estimates of the gradient can be beneficial for the generalization of the model. But we found, and this was the ICAS paper, that if we did a simple linear warm-up of the learning rate, where we start from 0.1 and work our way up to 1 for 10 epochs, and then an exponential decay of the learning rate, we could get basically the same performance as a serial implementation. So on the right-hand side, the black trace shows held-out loss versus training epochs for over 16 epochs with a batch size of 256. And then the orange trace is showing a batch size of 2,560 with this specific learning rate schedule. And the good news is that, indeed, we can get similar performance. And what we showed in the ICAS paper is by doing this, we could get the training down to 11.5 hours on, I believe it was 32 GPUs. So what happened after that? What happened after that is that Wei made an interesting observation that we're still trying to come up with a theoretical explanation for, which is that he found that he could grow the batch size using this asynchronous algorithm well beyond what was feasible with the synchronous stochastic gradient. So what I'm showing on the left chart here is a plot of held-out loss versus training epochs. The big black trace is the baseline serial implementation going for 16 epochs. The set of red traces, there's one here for the batch size of 4096, and then a whole bunch for larger batch sizes up here correspond to the performance of the synchronous stochastic gradient algorithm. So you can go up to 4096 and still get competitive convergence, but as soon as you go to a larger batch, all of a sudden the network doesn't converge at all. But if you use the asynchronous algorithm, which are the green traces here, we again see that we can grow the batch sizes significantly, even up to 12,288 samples, and still get good convergence performance. Like I said, this is an empirical observation at this point. We don't fully understand why this occurs. The supposition is that there's effectively a smoothing of the loss landscape introduced by the asynchrony, but the practical implications here are clear. We can blow up our batch sizes even further and take advantage of a larger number of workers and thereby train faster. Yes?
The orange curve on the bottom corresponds to the smallest batch size.
Right. Yeah, 4096 synchronous is this orange trace right here. And then, but as soon as you double it, it doesn't converge. Sure. Thanks for asking. And then the other trick that we have here is to look at matching the algorithm that we use for training to the machine architecture. So in many high-performance computing systems, you have this non-uniform network performance. So within a single compute node, which I'm sort of drawing here as these closed cyan boxes, you have very, very high-speed interconnect between the GPUs. So often you have NVIDIA and NVLink communication between the GPUs. You have extremely fast, high-bandwidth communication. And then you have something slower between discrete servers, either high-performance Ethernet or InfiniBand. So we can take advantage of that by saying, okay, within a single compute node where you have the really, really high-speed communication, you can perform synchronous stochastic gradient descent. So conceptually, each node will form sort of a superlearner. It's operating in parallel, but there's synchrony within that superlearner. And then between nodes, you can run the asynchronous stochastic gradient descent that has limited communication and maps better onto the somewhat slower communication between the compute nodes. And we're calling this scheme hierarchical adaptive, hierarchical asynchronous distributed parallel stochastic gradient descent. It's really getting to be a mouthful. But it works. So this is showing the scaling performance of this hierarchical algorithm using batches of 128 samples per GPU, going from one GPU all the way up to 64 devices. The blue trace here is showing the ideal case, which would be a purely linear speed up. And we can't do that, but we could still get a pretty good speed up, pretty good efficiency per added GPU with this algorithm. And this is it on a piece of hardware that's basically like a chunk of the Summit supercomputer. So we have 8 servers interconnected with 100 gigabit per second Ethernet, 18 Power 9 CPU cores per server, a terabyte of RAM, 8 NVIDIA V100 GPUs per server, and high-speed interconnect, not NVLink, but PCI Generation 3. And this shows the software setup. And so kind of the take-home message here is we can go up to now 64 GPUs. We're using a batch size of 8192. We can get the training time down to 5.2 hours using this high-speed hardware. And the performance is basically the same as the serial version, but now you can actually do experiments and try to optimize your models further. So that wraps up this portion of the talk. So if anybody has any questions, I'll take them now. Otherwise, I'll move on to the more theoretical work. Shinji.
I have a question. Is it based on VS? Do you have some comment for the CNN or PDNN or transformer? These questions is the same or different?
So this asynchronous algorithm has been applied in the image processing domain as well. So it definitely works well with convolutional networks, with ResNets. I'm not aware that anybody's tried anything like transformer on this. And in fact, one line of research that we're interested in doing is looking at other models and also looking at end-to-end models rather than the hybrid models. But that's still work to be done. Yeah?
Would there be any advantage in changing the batch size as you go through the epochs?
So that's also an approach that's been done. In fact, some really early work by Microsoft was doing that, where instead of scaling up the learning rate, they simply started with a relatively small batch size and grew it. And in some ways, they're somewhat equivalent approaches. But we found it more convenient to have a constant batch size and just monkey with the learning rate. But yeah, they're very similar. Hakan. We haven't tested Atom in this line of work, but there's some other work at IBM using a slightly different algorithm where, the learners are using Atom instead of stochastic gradient, and we can actually get fairly similar performance in terms of training time versus number of GPUs and word error rate. That's also work that's been submitted to ICASP and hopefully will appear. Okay, I'll move on to the second part of the talk. This is a plug for the interspeech paper. All right, second part of the talk. So this is completely different now. We're not going to worry at all about training networks quickly, but really this is an effort to understand what's going on inside of these models using tools from information theory. So this is joint work between IBM Research and a couple of people at MIT, Yuri Polyansky, who is a professor in the EECS department, and Ziv Goldfeld, who at the time of this work was a postdoc at MIT working with Yuri and has now gone on to Cornell University as a freshly minted professor. And this is work that was done under the MIT IBM Watson AI Lab. So, as we all know, deep networks have been extremely successful on a wide number of practical problems, but the theory is still trying to catch up. So we're still really trying to understand what's going on inside of these models. There's a lot of open questions about how these models learn, what they're learning, what the meaning of different layers in these networks are, and so on. And there's been a number of attempts to try to analyze deep learning from a wide variety of perspectives. So one line of work has looked at the structure of the loss landscape of these deep networks. And the general theme there is that if you make certain assumptions, you can often show that the local minima that are found by algorithms like stochastic gradient are not that far off in terms of loss from the global minima, and that the local minima are relatively easy to find. So an example of that work would be Anna Koromanska's work that was done at NYU a couple of years ago. There's work that relates especially rectified linear networks to wavelets and sparse coding. There's a really interesting line of work on adversarial examples, which is this observation that if you have a trained classifier, you can find very, very small perturbations in the input space that will cause the classifier to output high confidence incorrect outputs. So that's actually an interesting counterexample of sort of maybe an Achilles heel for deep learning at the moment. And then there's been a line of work looking at information theoretic approaches to deep learning, and that's kind of where this work is going to fit in. So just to get a little bit of notation out of the way, I'm going to be focusing in this talk on deep classification. So the assumption is that you have some input X represented by a large vector of features. The features are typically going to be reals. We want to assign a discrete label Y to each example where that Y is drawn from some finite set of labels. And then I'm going to denote the different representations in the network by T with a subscript that corresponds to the layer number. So the input layer, which is just the features, will be T0, then the first hidden representation T1, T2, and so on. And we're going to focus on deterministic classification tasks where each representation is just a deterministic function of the layer before. So if you have a multi-layer perceptron, this is just going to be, weight times the input plus a bias put through some sort of a nonlinear function like a logistic or a rectified linear unit. A convolutional network would be very similar, except that you have more limited connectivity. So there's a fairly old idea out there, dates all the way back to 2000, which tries to take an information theoretic perspective on learning in general. And the question that was being asked in this work was, if you're trying to do classification, if you've got pairs of features X and labels Y drawn from some distribution, and you want to have a classifier that does some sort of processing on X, learning a representation which we'll call T from those features, and then performs a classification based on this representation T, what are the properties that you would like T to have? And the information bottleneck theory puts forth two answers. The first is that you want the representation T to have the maximum mutual information possible with the labels Y. And that makes sense. You can actually bound your error rate in terms of this mutual information term. And then the other idea that's put forth is that you want to minimize the mutual information between the representation T and the input features X. And the intuition here is that you want the classifier to be insensitive to variability in X that doesn't have anything to do with the class labels. So it's an argument for Bender generalization. Obviously, you can't drive this to 0 because then you don't get good mutual information with your labels, but you can either cast it as a constrained problem where you say, okay, we want to minimize this mutual information subject to a maximization here, or set up basically a Lagrangian formulation where you want to optimize the difference of I of t and y minus some scaled version of I of t and x. Now, this theory was extremely successful in the 2000s in the case of doing supervised clustering, especially on text. And it's also been quite successfully applied to deep learning with stochastic models. So there's this work by Alemi and colleagues on what they call the deep variational information bottleneck, and this work by Achille and Sawato on information dropout. And it takes directly this information bottleneck idea and applies it in the stochastic case. But of course, most deep learning models are deterministic. So what about applying this theory to deterministic models? And there was some recent work trying to do this as well. And there was this very interesting observation made where if you look at the evolution of these information values over the course of training, there was this observation made that the training appeared to proceed in two phases. So this plot here on the right is showing what's called an information plane, where it's the mutual information between hidden representation T and labels on the y-axis, information between the input and the hidden representation on the x-axis. Each of these traces corresponds to a different layer in a network with the, let's see if I've got this right, the rightmost trace corresponding to the input layer, and then as you move to the left, you're getting deeper and deeper layers that are farther from the input. And what was found was this pattern where they would see this information between x and t first rise along with y, and that would correspond to these points here. So each point here corresponds to an epoch of training, and then at some point, mutual information between the hidden representations and x would hit a maximum and then start decreasing while the information between the hidden representations and the labels continued to increase until you had convergence. And this was observed on a number of tasks and a number of networks. And it's important to note that in all of these studies, the mutual information was estimated by doing binning. So you'd take your hidden representation, do some sort of a discretization, and then basically compute an entropy, and that would give you this mutual information term. So this work that I'm talking about started when these mutual information, when these information theory guys at MIT looked at this work and said, wait, something's wrong here. And what's wrong is that these networks are deterministic. And in many cases, These networks have monotone nonlinearities like hyperbolic tangent or sigmoid. And the problem is that then what you have is you have an invertible function. The function that goes from the input features x to some hidden representation t is completely invertible if you assume sufficiently high precision arithmetic. And in that case, if x is drawn from a continuous random variable, this mutual information term is actually infinite. If x is drawn from a discrete random variable, which is actually the case that we have most of the time because we have finite training sets, then this mapping from input features to some hidden representation is almost surely injective, and the mutual information term becomes just the entropy of the input features. So to illustrate the concept of a discrete random variable, what I'm showing here is if you assume you have one of these toy problems of two interleaved spirals with each spiral labeled with a different, different class label, you have a finite number of samples. So even though the DNA may do some really, really elaborate mapping of those samples, it's still going to be discrete in the sense that you have a one-to-one correspondence between training samples on the left and samples in the hidden representation space on the right. So the problem here is that in both cases, this I of xt term is independent of the DNN parameters. So these plots that show it changing over the course of training can't possibly be right. So what went wrong? And the answer is that this binning estimator for mutual information is not particularly good. So what this is showing is, for a specific network that I'll talk about a little bit more, what happens if you change the bin size in this estimator. And this is for a problem where we have a discrete x sampled from 2 to the 12 different elements. So your entropy, if you're using natural log, is 8.32. And if we look at the large bins, if we look at these mutual information estimates over training, we see a lot of variability. But as you shrink the bin size, eventually you get over here and you see that everything stays up where you would expect at 8.32, except here at the end in the last layer. And again, it's just because samples get put close together to the point where the bins don't resolve differences between them. So in other words, the only way to get a reasonable estimate is to have really, really small bins, which becomes computationally expensive. So when people didn't do that, they got phenomena like this. But the real picture is over here. This I of xt doesn't change. So, of course, lots of deep networks aren't necessarily purely injective. So, for example, rectified linear units are not invertible. And max pooling, which is a very common operation in computer vision, is also not invertible. But interestingly enough, even with models that include that, if you have a finite training set, it's very, very hard to find non-injective behavior. So this is an example with a very, very small classifier trained on the MNIST digit recognition task, where we take input representations, do 2 bins, just thresholding is 0, and we look at this entropy estimate. And what we see is that it stays very, very close to log of the number of input samples, even with these non-invertible, even with a non-invertible max pooling operation. We still have hyperbolic tangent. So what can we do to try to use information theory to understand deep learning? Is there a way to formulate a DNN framework where this mutual information between input features and representations makes sense? Can we estimate the mutual information efficiently? And what can we learn by tracking it during training? So that was basically the project that we were doing. And the good news is that it actually wasn't too hard to come up with a framework where it did make sense to do mutual information estimation between input features and hidden representations. What we have to do is we have to inject some noise into the network. So we start with a deterministic network, and then we add, at the output of each hidden layer, a little additive Gaussian noise source with 0 mean and a controllable variance. You can then do analysis and show that this network now becomes a channel that's parameterized by the DNN parameters, and the mutual information between input features X and hidden representations is now an actual function of the DNN parameters. So studying it might tell us something. This is, of course, only a useful step if these noisy networks perform in ways that are similar to the deterministic networks. So we did some work looking at similarities between hidden representations of noisy and deterministic networks for a number of cases of additive noise and also for dropout. And we found that as long as we kept the additive noise small, the hidden representations were fairly similar. What I'm showing here is cosine similarities to the noisy model. To the noiseless model, sorry. And we see a pretty good correspondence at the input layer and the output layer, particularly somewhat lower correspondences here, but if you do the math, if they were completely random, we'd be very close to zero with these high dimensionalities. So some correspondence. And if we look at the performance of these models, we also see that as long as the additive noise is small, you have similar performance on held out data. Interestingly enough, dropout gives, of course, the best held out performance and also in some ways shows, I guess in this case, the hidden representations are fairly similar. Okay, but the take-home message here is quite simple. Adding a little bit of noise to your network is not really going to change its behavior in any significant way other than making information estimation a sensible operation now. Okay, so how do we go about doing the estimation? If we assume that these x's are drawn from a finite training set or a finite test set and we're just uniformly sampling from that set, then the mutual information at some layer, one of these hidden layers, is going to be simply the entropy, the differential entropy of the layer minus the average conditional differential entropy of the layer, conditioned on the selection of the input features. What's important here is that there's some structure, which is that this hidden representation is a sum of two variables, S and Z are independent of one another, which means that the distribution of T here can be looked at as the distribution of S convolved with this zero mean Gaussian. That's the good news. But the bad news is that the distribution of these S variables is quite complicated. Because what they are the result of is a composition of noise sources and nonlinearities and so on. However, we can easily sample from these simply by drawing samples of X and passing them through the network. Which leads us to what we call the sample propagation estimator. So the idea here, I'm a little short on time, so I may hurry through this a bit, is that you can basically form a plug-in estimator for differential entropy by just drawing samples from some set, passing them through the network, and doing differential entropy estimation of based on point-wise samples. You can do it either using Monte Carlo integration or things like the Kolchinsky-Tracy estimator. We have some theory that shows that this sample propagation estimator achieves the best possible bounds that you can get, which unfortunately are exponential in D, but match the parametric estimation in terms of the number of samples you take. What this means in practice is that we can only do this operation on really, really small networks because of the exponential factor here in D, D being the dimension of your hidden representation. Okay. So let's try to get some intuitions about what's going on here. And we're going to do it by looking at the simplest possible network you can imagine, which is a single hyperbolic tangent neuron with tradable weight W and bias B. You've got samples X coming in, and we're going to do a really, really small toy case here where we assume that X can only take on 4 values, plus or minus 1, plus or minus 3. The values of minus 3, minus 1, and 1 are given one label, and the value of 3 is given another. We're going to do mean squared error loss. What happens as you train is that the weight and the bias will adjust themselves so that the hyperbolic tangent is pushed over to discriminate between the 1 and 3 here. So training just shifts and sharpens this transition. What's nice, though, is because this is an invertible operation here, this hyperbolic tangent of Wx plus b, and mutual information is invariant to invertible transformations, we can say, okay, well, the mutual information between x here and t here is the same as the mutual information between the output here before the noise and the sum of the noise and this output. And this term here just is simply information transmission over a channel with additive white Gaussian noise, which is a well-studied problem. So what this means is that the information between the input features x and the hidden representation t, in this case, is simply the amount of information that you can transmit over the additive white Gaussian channel with variance beta squared. I guess I got the notation wrong there. Using symbols, minus 3w plus b, minus w plus b, w plus b, and 3w plus b. Again, because we're drawing x from this discrete set. If we look at these Gaussians as we do training, what we see here is that the Gaussians start out kind of clustered around 0 because we started with small random weights. They all start moving, and eventually the one that corresponds to the different label starts to get separated out and pushed apart, and that the other 3 start to get pushed closer and closer together. If you look at mutual information versus training, what you see is it goes up, and then at some point, as these Gaussians get closer and closer together to the point that they can't be resolved, this mutual information term drops. In other words, what's going on here is that as training proceeds, the first 3 symbols, the minus 3, minus 1, and 1, get represented by these Gaussians that become closer and closer together, harder and harder to resolve. So there's effectively a clustering going on. Yeah, 3 minutes. Okay. We see similar behavior in other toy examples. So this is a binary classification task. And what I'm showing here is mutual information in this middle trace, training and held out loss on the bottom. And then these are scatter plots corresponding to specific points during the training. So here, where this mutual information term is near a maximum, at epoch 28, you see sort of a very uniform distribution of samples. Here, where there's a little bit of a minimum, there's some clustering, another maximum, again, more of a uniform distribution. And at the end here, where information is dropped again, we see examples clustered sort of at corners of this space. We see somewhat similar behavior in a different network where we do some regularization, but since I'm out of time, I'm going to skip this. But the end of the story is what's going on? What was being seen in the previous work that was doing binning? And the answer is that the binning estimator was not really measuring mutual information, but it was measuring clustering. That as the network trains, what tends to happen is that samples with the same class label will cluster together in the hidden representations successively. The binning-based mutual information estimator was simply tracking that clustering, and that's actually the mechanism that's driving this observed behavior. We have some additional evidence where we looked at noisy DNNs and compare the binning-based estimator with the proper mutual information, and we see that they evolve in somewhat similar ways. But yeah, just to wrap up, in deterministic networks, this mutual information between input features and hidden representations is basically vacuous. We can formulate an auxiliary noisy network framework where we can estimate this in a principled and reasonably efficient way. And we show that the previously observed decrease of mutual information between features and hidden representations in noisy networks corresponds to clustering. And in fact, the same clustering occurs in deterministic networks. And also, this compression, this loss of mutual information between the input and hidden representations may not necessarily imply better generalization. So that actually calls into question some of the original information bottleneck work, at least in the case of deep learning. But that's still something we have to study more. This has been written up. There's an ICML paper and an IEEE transactions paper, both available in archive, and I can take questions at lunch.